All right. Okay, so let's go ahead and get started with 6.1. All right, so 6.1 is a topic called area between curves. And so I wanted to spend some time thinking about what we know versus what's new. So what we know, what we did in basically all of chapter 5 was think about how we could find the area between the curve and the x-axis. And so that was a phrase that we saw a lot, that we were looking for the area between the curve and the x-axis, okay? And so that's what we were finding when we set up our integral to be something like this, the integral from a to b of f of x dx. And so anytime we saw that notation, we knew that we were finding the area. And so in this diagram here, we're just looking for this area around A. Okay. Now, if we kind of look over here, this right-hand side tells us what's new, okay? So what's new is gonna be that instead of just having one curve like we had in chapter 5, now there's gonna be two curves, okay? And so specifically, if we look at this diagram right here, we've got that f of x curve on the top, okay? And then we have this second curve on the bottom, this g of x curve. And what we're trying to do that's a little bit different from before is now we're trying to find the area that is sort of sandwiched between these two curves. Now they still give us a starting point, like we're still starting at A and we're still finishing at B. Those two still stay the same. But what's different is that we just have an actual second curve, okay? Now, if we think back to chapter 5, we had two curves then as well. We had this top curve, this f of x curve. And then what's sneaky here is that our bottom curve was actually the same every single time. The bottom curve was actually the x-axis. Okay, so this x-axis was really our g of x. Now, let's take a look at this smaller diagram here, okay? So when we think about finding the area between a top curve and a bottom curve, what we're doing is we're taking that distance between the two curves. So let's say I find this distance right here, okay? And I find that area of that rectangle. And then I find the area of the rectangle next to it. And then I find the area of the rectangle next to it, okay? And if I keep going all the way across until I get to the end, all right, then what I found is the area between the two curves, because I've taken this area, I've sort of divided it up into really, really skinny rectangles and added those all up together. And so one thing that we should realize is that when we see this dx at the end of our integrals, the reason that symbol is so important is because that's really telling us how wide our rectangles are. And so if we look in this picture right now, I think it's a pretty good estimate of the area. But what would happen if instead of however many rectangles I had here, I had like an infinite number of rectangles? So I had like one really skinny rectangle like this, and then I had another one like right next to it, and then I had another one right next to it. what do you think would be better? The one with the that we have the picture of right now, or if I had a bunch of really, really skinny rectangles?
The skinny rectangles.
Yeah, the skinny rectangles. And so that's what this whole dx thing or delta x is. The smaller we make delta x or dx, the more accurate it's going to be. And that's why when we take this integral, we're not dividing it into rectangles anymore, but we're saying the process that we're doing is basically turning it into rectangles. And these rectangles are so skinny that we almost think about it just as the height difference between the top curve and the bottom curve. So just the height difference between the top and the bottom. And that height represents the height of the rectangles, and then the width of the rectangle is just infinitely skinny. So with that concept in mind, let's write down two super important formulas. So we're going to see a bunch of cases that look like this diagram right here, okay? And when we see a situation like this is what we call finding an integral with respect to x. And what it means is that your rectangles that you're imagining are perpendicular to the x-axis, okay? So the rectangles are perpendicular to the x-axis. Now the formula that we're going to use when we see this kind of situation is, in order to find the area, we're going to take the integral from a to b of the top curve minus the bottom curve. And because all of our rectangles are perpendicular to the x-axis, we need a dx at the end, okay? Area equals the integral from a to b of the top curve minus the bottom curve dx. Now, once in a while, we'll see pictures that almost seem more sideways, okay? And that will be clear to us when we see rectangles that are perpendicular to the y-axis, okay? So it's almost like if you look back at this picture right here and you kind of turn your head sideways and imagine that they were all going perpendicular to the y-axis, that's what that would look like. And the formula that we want to use in those cases is going to be the integral from c to d. So we're using different letters here, okay, from c to d of the right curve minus the left curve. And because all of our rectangles are perpendicular to the y-axis, we're going to seal this off with a dy. A couple quick notes about these formulas, okay? In the with respect to x case, a and b are x values. However, in the with respect to y case, c and d are y values, okay? So if there's a dx at the end, your bounds need to be x values. And if there's a dy at the end, your bounds need to be y values, okay? So that's one thing that definitely needs to match in your equation. The other thing that needs to match is this, that your top curve and your bottom curve in the dx case are oh my goodness, are equations with x in them. Okay, so it could be like x squared. It could be like 2 to the x. It could be like sine x. All of those are equations with x in them. But when we look at the ones with respect to y, the right curve and the left curve are equations with y in them. So for example, you could see an equation that maybe instead of saying sine x, it would say sine y. That would be one you could use with the respect to y. Or maybe it's like y squared minus 4y. That would be a really good indication that you want to do it with respect to y. All right, so let me zoom back out for a moment. All right, so this is sort of conceptually what we're going to be doing, but we're going to spend the rest of today working through a ton of examples, okay? And so with these examples, what I really hope that we practice and are able to demonstrate on this final exam include being able to make a decision. Do I set this up with respect to x or with respect to y? Usually you can use both of them will work, like both with respect to x and with respect to y will work. But usually one of them is significantly easier than the other way. And so that's part of the decision-making process that I want us to practice, okay? So choosing the method. I also want us to really be familiar with drawing diagrams, okay? So if you have Desmos available to you, that might be a good tool to work with today, but also when you're practicing. I think in all the practice videos, it should already have a graph from Desmos there, but it might not be a bad idea to kind of practice being able to graph. All right, so let's get started with some practice problems. All right, so example number 1. It says, find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. And so what we're going to do is start off with a diagram. Okay, so this is similar to a lot of the sort of more challenging problems we've seen where it's like, let's just start with a picture. Let's see what this looks like, okay? Because in order to decide whether we're doing with respect to x or with respect to y, we need to see, like, are the rectangles perpendicular to the x-axis or are they perpendicular to the y-axis? Meaning, do we see a very clear top curve and bottom curve, or do we see a very clear right curve and left curve? And so what I'm going to have us do is this. We're going to try and sketch this without Desmos first, okay? And then we're going to come back in and make sure we get an accurate graph. So let's start with this one, y equals x squared. Pretty straightforward. What shape do we have when we have y equals x squared?
Parabola.
We have a parabola. Good. So I'm going to go ahead and just sketch a parabola. All right, so I've got my parabola, and let's go ahead and take a look at the second equation. So in our second equation, we have y equals 2x minus x squared. What shape is that?
Isn't it also a parabola?
It is also
facing down?
It is facing down. And how do you know that?
Because it's negative in the middle,
Yeah.
or it's 2x minus.
Yeah, that x squared part is negative, okay? Now, one thing that is really useful about knowing how to factor quickly. So for example, I look at 2x minus x squared and I'm like, well, I could factor out an x and then I get 2 minus x, is that actually helps me sketch the parabola pretty quickly. I know that this parabola will cross the origin at 0 and at x equals 2, because those are the two numbers that give me a y value of 0. So I know that my parabola is upside down. I know it goes through that point, and I know it goes through a point here at 2. And then I can sketch in the rest of it, so I have something that kind of looks like this. All right, so now we've got our graph, and our job is to figure out the area that is in between the orange parabola and the green parabola. So I can think about it kind of like this. That could be one really skinny rectangle. This could be another really skinny rectangle. This could be another really skinny rectangle. Then I could have an infinite number of skinny rectangles in that area. And so because I'm looking at these rectangles and thinking, okay, these rectangles are perpendicular to the x-axis, that's a good clue that I want to use the with respect to x formula. So I'm going to go ahead and write down this formula, the integral from a to b of the top curve minus the bottom curve dx. So that's going to give me the area equals the integral from a to b of the top curve minus the bottom curve dx. Now, if I look at my equations, y equals x squared, does that equation have the x in it? Like x squared has an x in it, right? What about the green one, 2x minus x squared? Is that equation an equation with an x in it?
Yes.
Yeah, okay. So it's sort of, I can look at the diagram and see that I'm drawing vertical rectangles, or I can look at my equations and say, they've given me the equations with the x's in them already. So those are sort of two different clues that I want to do this question with respect to x and not with respect to y. So based off of what we have here, let's see what we can fill in. Which curve would we say is on the top of those blue rectangles?
Y equals 2x minus x squared.
Good. So I'm going to put the green curve here. So 2x minus x squared. That's the top curve. And again, I know that from the diagram. And then minus, that leaves the orange one as the bottom curve, x squared. Whoa. Okay. But one thing that I don't have yet is I don't have my bounds. Like I don't know where to start and you don't know where to stop. So if I kind of zoom back into my picture, let's take a closer look. So I'm going to start where the curves first intersect. So that's going to be right here. Okay. At that value, I'm going to be starting to count my area. When I get to here, okay, that's where I'm going to stop counting my values. And let me actually do that in different color. So I'm going to start counting here, and I'm going to stop counting here. So this first pink line is my A, and this second pink line is my B. What number do we think A is in this case?
0.
0. Okay. Why is it 0?
We know x squared goes through the origin at 0, 0, and then we saw that one of the x values is x equals 0 for the other equation.
Yeah, yeah. This one is at 0. Okay. And what I really appreciate about what you said is that it's 0 because this is the x value at that point. So now we need to find the y value at that point. Or sorry, not the y value. We need to find the second intersection point. And one way to find the intersection point is to graph it on Desmos and see sort of like where it is. But another way to do it is that we're just going to take our two equations, the orange one and the green one, and we're going to set them equal to each other. Because when they're equal to each other, that means that those two functions have the same coordinate. Okay, so to find b, we're gonna take squared, which is the orange curve, and we're gonna set it equal to 2x minus x squared, which is the green curve. And we're gonna solve for x, okay? So I'm gonna move this x squared to that side, so I'll get 2x squared equals 2x. I want us to be really careful here. I don't want us to just divide the 2's away, okay? I actually want us to move everything to one side and set it equal to 0. And I'll show you why in just a second. So from here, I'd like us to factor. So 2x, x minus 1 equals 0. And now that it's factored, I can set each part equal to 0. So 2x equals 0 and x minus 1 equals 0. And so when I solve the first equation, I'm going to get x equals 0. And when I solve the second equation, I'm going to get x equals 1. This is our A, and this is our B. All right, so A is 0 and B is 1. But the reason why I didn't want us to divide way earlier in the problem, let me show you that right now. So what happens if you divide? Let's say you're like, I'm going to divide a 2 away from both sides. So you get x squared equals x. And then you're like, yeah, now I'm going to divide both sides by x. And you get x equals 1. Well, that's not wrong, right? That was part of our answer. But that's just it. It's only part of our answer. Okay? So this will only gives you one answer. Whereas this method, this one gives you both. And so that's going to be important as you kind of go through these problems. You want to make sure that if you're going to put the work into setting up these equations and finding your bounds, that the work you do gives you both bounds and not just one of the bounds. Okay. So let's go back to our problem. We have our A is 0 and we're going to have our B equals 1 now. Right? So I'm going to come back to my equation and I'm going to put a 1 at the top. All right. Before we move on to solving, are there any questions about this setup so far, like what we have in the equation?
So for to find b, it's always going to be that we need two x's, correct? Like, so that's why we always want to make sure that we don't just try to divide, like you said. That's not the proper way to do it. Instead, make it equal to 0.
Yeah, so the reason why we want to make it equal to 0 is in this case, we already knew our A, So we really only had to find B. So in this
Uh-huh.
case, it would have been fine to just do the work in the red.
Mhm.
However, what if you run into another situation where you don't know A and you don't know B, and it's hard to tell from the diagram? Then in that case, it's really important that you move everything to one side, set it equal to 0, so you don't lose a solution.
Okay, gotcha.
Okay, cool. All right, so on an exam, I'm definitely looking for the setup, okay? I want to know, do you have a diagram that supports your work? Do you know which one's the top curve and which one's the bottom curve? And does that match your diagram, okay? So from here, once we've got our setup, and we know that the 0 is an x value, and so is the 1. We've got all x's in our equation, and we have a dx at the end. Now we're ready to solve, okay? So we really need to make sure that everything matches before we go off and solve. So we have the integral from 0 to 1. And I'm going to simplify the integrand by getting rid of the parentheses. So I will have 2x minus x squared minus a second x squared dx. And I can simplify that even more to say the integral from 0 to 1 of 2x minus 2x squared dx. Now, when we integrate, we need to use the power rule. So the integral of 2x is x squared. And the integral of 2x squared is going to be 2/3 x cubed. And I'm going to draw the vertical line, and I'm going to put a 1, and I'm going to put a 0. Now I'm going to use my fundamental theorem of calculus part 2 and plug in my bounds. So first I'm going to plug in b, so 1 squared minus 2/3 times 1 cubed minus 0 squared minus 2/3 times 0 cubed. And this is going to give me 1 minus 2/3 minus 0 minus or plus 0. And so this will leave me with an answer of 1/3. And so 1/3 represents the area between the orange curve and the blue curve when we start at 0 and we end at 1. Okay, any questions on example 1?
Where'd you get the 2/3 again? I'm sorry.
From here?
Yeah, right above it.
Oh, sorry, that 2/3.
Yes.
Okay, so if I'm finding the integral of 2x squared, I have the constant. For the x, I add a power, and then I have the reciprocal.
Got it.
Okay, other questions on example 1?
Do we need to add like units at all to our answer? Like when finding area and other times we do like inches squared or like inches or anything like that? Do we
That's
have
a great question. No, we don't actually, because these are more like we don't have a context for it necessarily. We're just saying like, here's some pictures, let's find the area in between them, but we don't know like what we're counting by. So it's not like we're measuring something and then trying to, like we're measuring something with inches or centimeters. It's
Okay.
just sort of like a more conceptual, like here's our area.
Okay, perfect. Thank you.
Other questions? Okay, let's move on to example 2. So example 2 says that to determine the area of the region between the two curves, y equals x squared minus 24 and y equals 1. So let's go ahead and sketch our diagram. Okay. And we'll kind of keep it constant. Let's say that our first curve is going to be in orange and our second curve is going to be in green. So what can folks say about the shape of the orange curve? The shape, and maybe like what are some important points on that curve?
The parabola, and it's down 24 units on the y-axis.
Yeah, exactly. So this tells us that it's a parabola. And this minus 24 says I move that parabola down 24 units. Okay. So let's take the orange and let's go ahead and sketch a picture. Oh, that's not bad for a Thursday morning. I've not been sleeping well this week, so I feel like not sure about the quality of the graphs. But again, this would be totally fine. And if you wanted to sort of mark this off for yourself as 0, negative 24, that could be valuable information too. Okay. Now, if we wanted to sketch the graph of y equals 1, what does that look like?
Is it just a line at y equals 1?
Tell me which direction that line is.
Positive? I don't know.
Oh, sorry. I meant, is it like horizontal or vertical or diagonal?
Oh, horizontal.
Horizontal. Okay, cool. Yeah, so when we see this y equals, we really want to connect that with it's a horizontal line, and it's going to be at positive 1. So when I draw this green line, I can mark it off like here. Okay. All right, so I've got my diagram now. From this diagram, what we did last time was kind of draw rectangles, or like really skinny rectangles, okay? Now, the catch to drawing the rectangles is this. We want to try and draw a rectangle that goes from one of the curves to the other curve. We don't want to do something where it's starting at one curve and it goes back to the same curve, okay? So don't write this down, but I'm going to draw what would be like not a great picture, okay? So if I wanted to draw my rectangles and I was like, here's one rectangle, here's another rectangle, here's another rectangle. The rectangles that I'm drawing are horizontal, so I would want to use dy in this case. Like if I kept the rectangles that way, I would be telling whoever's looking at my work that I'm planning on doing dy. But the problem with this is in order to do dy, I need to have a right curve and a left curve. And for all 3 of the rectangles I drew, the right curve is the orange curve, but the left curve is also the orange curve. So if I'm going to do right minus left, I'm going to have the orange curve minus itself, which is going to give me 0. But when I look at this picture, I know that there's an area. So to me, that is a really good clue that that's not the best way to approach this situation. So I'm going to undo my rectangles, and I'm going to draw them vertically. And when I draw the rectangles vertically, like this could be one, this could be one, that could be one. And when I draw vertical rectangles, what I'm telling whoever's looking at my work, or what I'm telling myself, is that I want to use dx, and therefore I need to have a top curve and a bottom curve. And so when I look at all three of these blue rectangles, what's the top curve?
Y = 1.
Yeah, it's the green one, right? It's y = 1. And the bottom curve is the orange one. So all three of these rectangles, in fact, any rectangle that I drew would have the same top curve and the same bottom curve. And that's really helpful when we want to set up a formula, okay? So because the vertical rectangles work out a little bit better than the horizontal ones, I'm going to set up my area to say the integral from a to b, where a is an x value, b is an x value, of the top curve minus the bottom curve. And at the end, I'm going to make sure I have a dx, because that is officially saying the width of my rectangle. Now, like the last example, I can actually go ahead and fill in my top curve is going to be 1. And then minus the bottom curve, going to be the x squared minus 24. Okay, so bottom curve and top curve. Now I need to find out my a and my b. So let's go back to our diagram. I know that here is the first time they cross because we look at this from left to right. And this x value will be my a. And I know that they stop sealing off that area at this point, and that is going to be my b value. So I need to find both my a and b value this time because it's not as easy to see them from the diagram, okay? So to find a and b, we're going to use the same idea that we did earlier, which is we're going to take our two equations and we're going to set them equal to each other. So I'm going to take my x squared minus 24 and I'm going to set it equal to 1. Okay. There are probably at least 2 different ways that we could solve this one, and let's see how they both work. Okay. So in one way, I'm going to follow what I did in the previous problem, which is move everything to one side, set it equal to 0. So that would be x squared minus 25 equals 0. And that factors into x plus 5 and x minus 5 equals 0. So I know that x equals negative 5 is one intersection, and x equals positive 5 is my other intersection. So a is negative 5 and b is positive 5. Now, I know a lot of us are not super comfortable with the factoring, and we kind of do everything we can to avoid factoring. But I do think it is useful in this case because this pattern of like a squared minus b squared comes up so often. But an alternative in this case might be like, you're like, well, I'm just going to move that 24 to the other side. So I get x squared equals 25. Great. And I'll just take my square root. And if you've not made this mistake, you might be one of the few people who's never made that mistake. Right? So now what we're running into here is it's really easy for us to lose that second solution. So if you use this second method, what you need to be super aware of is that when you take your square root, you better put that plus and minus in there right away. Otherwise, you're only going to get one answer, okay? All right, so we found our A and our B, and we can go ahead and put in a -5 at the bottom of my integral symbol and a +5 at the top of the integral symbol. Okay. Are there any questions so far about the setup? Okay. So let's see what our integral looks like. The integral of -5 to 5 of 1 minus x squared minus 24 dx. Correct or not correct?
Not correct.
Not correct. What's wrong?
It should be plus 24.
It should be plus 24. Okay, so we really want to be careful about that. Am I distributing everything I need to? So like this one right here, I don't need parentheses for that. I know that. But I bet a lot of us are going to write the second one also without parentheses. And then we end up in a situation where it's not going to work out because we made a sign mistake at the very beginning. Okay, so be really careful about that. And now we can combine our like terms. So we'll get 25x squared dx, okay? And now we're ready to take our antiderivative. So when we take our integral of 25, what do we get?
Zero.
0.
No.
What?
When we take the
25x.
20, yeah, the integral, all right? And that is something that we want to be really careful of. There were a couple folks on that last exam who were just working too fast or, you know, forgot to double check that one. And you're like, yeah, it's 0, obviously. But one of the things about that probably makes Calc 2 a little bit harder is what, like literally in the same problem, you could be doing a derivative and then later on you're doing an integral, and you really have to be sharp on which one's which, okay? So we have 25x minus, what's the integral of x squared?
X cubed over 3.
X cubed over 3. All right. Now that you have this, you can draw the line, put the 5 at the top and the -5 at the bottom. Okay. All right, let's plug in our bounds. 25 times 5 minus 5 cubed over 3 minus 25 times -5 minus -5 cubed divided by 3. Okay, now if you haven't watched the video yet, I'm going to do this the same way I did in the video, okay? Now, I know that we all have calculators. We can type this in, call it a day. In fact, we can even have our calculators take the decimal and convert it to a fraction for us. But I really want us to know how to sort of do this by hand, but also at the same time make the least amount of work for ourselves, okay? So you can sort of simplify as you go, but what I tend to do is sort of like group my like terms. And what I mean by that is any term that's like a whole number, I tend to keep those together. And any term that before I simplify is a fraction, I kind of keep those together. Okay, so let's maybe simplify this a little bit and I'll show you what I mean. So 25 times 5 is 125 minus 5 cubed is 125, and then it's 5 cubed over 3. Then I'm going to subtract that, and I'm going to subtract that. So minus 25 times -5 is -125 minus, is this going to be positive 125 or negative 125?
Negative.
Yeah, it's going to be negative 125 over 3. Okay, so now let's distribute our signs. So I've got 125 minus 125 over 3 plus 125 minus 125 over 3. Now, when you're working on this final exam, please show me these steps, okay? If you're telling me, all right, I could just do it in my head, I kind of need to see the documentation. And that doesn't necessarily mean that I don't believe you. It means that because we're remote, I need you to leave a trail of breadcrumbs. Like, help me understand your thinking, all right? Now, from here, I think it's a little bit more clear what sort of like terms I have. So like 125 and 125 are both whole numbers. So I'm going to combine those together and I'm going to get 250. Separately, negative 125 over 3 and negative 125 over 3, they're both fractions, but more significantly than that, they're both fractions with the same denominator, which means that I can combine them fairly easily because I don't need to change the denominator. And now I only need to change one term into a fraction with the same denominator. Now I only need to change this 250 into something over 3. So 250 is the same as 750 over 3 minus 250 over 3, which will give me a total of 500 over 3. All right, so here's question number 2 in its entirety. All right, so we started off with our diagram, thinking about what we know about graph transformations. We were able to pick, we wanted vertical rectangles, which meant that we had to use the formula integral from a to b of top curve minus bottom curve dx. And then we had to find our bounds. And once we found our bounds, we could start plugging in, make sure our antiderivatives were accurate, and then go from there, okay? So this is about as much work as I'm expecting to see on these kinds of problems, just to make that really explicit, okay? Are there any questions about example 2?
Take a break.
Okay. Well, let's take a look at example 3, and then after example 3, we will take a break. All right, so here we go. Example 3 says, find the area of the region bounded by the curves y equals sine x and y equals cosine x from 0 to pi over 2. So I'm going to go ahead and draw my graph. And I'm only going to draw the positive side because they already tell me that we're starting at 0. So 0 is my A. And then they're telling me I want to stop counting at pi over 2. So those numbers in the brackets tell you your starting and stopping point. Well, all right, so we've got y equals sine x, and we've got y equals cosine x. Now, it is completely fair game for trig functions to be something that you're expected to know how to graph, okay? Now, I know that this is an area that a lot of folks are not super strong in, so I would highly recommend that this get on your cheat sheet, all right? if we have our graph of sine, that actually starts at the origin, and I'm only going to draw one bump here. So it goes like this, and then it sort of finishes there at pi. And if I were to keep going, it would go below the x-axis and come back up at 2 pi. For cosine, it actually starts up at 1 and kind of goes like this. Okay. Now, let's add in a few other markers. So this, the cosine graph, crosses the x-axis at pi over 2. So that means that since pi over 2 is my b value, I'm going to sort of just mark that off as the end of what I'm finding the area of. And I can also mark off where I'm starting, which is at x equals 0. Then let's think about our rectangles, okay? So when I'm drawing the rectangles, if I look at my equations and it's already in terms of x, like I have sine x and cosine x, your best bet is to try the vertical rectangles first. So if I do the vertical rectangles here, top curve is the green one, bottom curve is the orange one, okay? Does that second blue rectangle have the same top curve and bottom curve as the first one?
No,
Why not?
because the green is under the orange in the second one.
In this one?
No, in the second.
Oh, okay, like if I drew like this.
Yeah.
Okay, okay. So that's actually really observant. So at some point, the green curve was on the top and then it becomes on the bottom. And at some point, the orange curve stops being on the bottom and starts being on the top. And that point is right here, right in the middle, okay? Now, I know that it's in the middle because I know that the sine and cosine have the same value at pi over 4. So another reason why it's important to know our trig functions, because it helps give us more information than possibly is on our graph, okay? Now, had I drawn the picture better, it might be more obvious to you that the area that's like right here with the solid blue lines, and then the area in that second region with the dotted blue lines, those two areas are actually symmetric, like they're the same area. So from 0 to pi over 4 is going to be the same area as from pi over 4 to pi over 2. When we set this up, we can set this up in 2 different ways. And let's set them both up, and then as a class, we can kind of choose which way makes more sense for us right now. So I know because I have vertical rectangles that I'm going to take the integral from a to b of the top curve minus the bottom dx. Now, one thing that would be very wrong to write is this. Why is that wrong?
Because the top and bottom changes.
Because the top and bottom changes. Okay. So by similar reasoning, this is also wrong, because at some point the top and bottom change. So that's something important to note about when we say top minus bottom, that it has to be the same function all the time that's on the top, and the same function all the time that's on the bottom. If they switch, you have a few different strategies to consider, okay? So let's just make it more obvious. No, don't do that. No, don't do that. Okay. So what can we do? Here's one option. So option 1. I can do this as sort of 2 separate mini problems. So I can say the area equals the integral from 0 to pi over 4. So the point where they switch of cosine x minus sine x dx. So that gives me the first region, plus the integral from pi over 4 to pi over 2 of sine x minus cosine x. Because as soon as they switch to a different top and bottom, I have to show that in my equation. So this is one option that we have. Another option, which you can only use in certain cases, including this one, is the idea of symmetry. So I can say that my area is going to be the integral from 0 to pi over 4 of cosine x minus sine x dx. That's that first area, but because I know it's equal to the second area at the end, I'll just go ahead and double it. So that's valid. If you wanted to, you could also find the area of the second one and double that. Okay, so option 1 is you split it up, you find area 1 and you add it to area 2. In the special case that they're symmetric, you can actually shortcut it and do option B, where you go from 0 to pi over 4 and then you double it, or you take the second half of the area and you double that. All right. So what are folks' thoughts? We want to do option 1, option 2. What do we think will be faster in this case?
Option 2.
Probably option 2.
Yeah. And again, you can't always use option 2, right? This is a case of only when it's symmetric. But if it is symmetric, you might as well take advantage of it, okay? And so I think what would be probably the most straightforward one, or the easiest one to compute, is this one. The reason why I'm picking the first one and not the second one is because having 0 as one of the bounds tends to be helpful, okay? It's a little less helpful with trig, but when I'm looking at polynomials like x cubed and x squared, it's really, really helpful. Okay, so let's take a look at what happens when we find the area from 0 to pi over 4 of cosine x minus sine x dx. So the integral of cosine x gives us what?
Sine x?
It does give us sine x, good. And the integral of sine x gives us negative cosine x. And then I'm going to plug in pi over 4, and I'm going to plug in 0. Now I would definitely clean this up to say 2 times sine x plus cosine x from pi over 4 to 0, right? So I would distribute that minus sign. And now I can go ahead and plug in my values. So 2 I have sine of pi over 4 plus cosine of pi over 4 minus sine of 0 plus cosine of 0. Now, if you're only going to write the 2 one time, please have parentheses around the whole thing. I did see a small handful of people who, again, maybe you were sort of working a little too fast on exam 3, and there was a case where like it was distributed to the whole thing, but you didn't. Or on the flip side, it wasn't distributed to the whole thing and you did distribute it, okay? So make sure you're making it very clear to yourself in your work what's happening. All right, time for those trig values. So I get sine of pi over 4 plus cosine of pi over 4 minus sine of 0 is 0, and then I got to distribute that minus sign, so minus cosine of 0 is 1. And this is going to give me 2. And let's see, when I combine those two, I have a half of a root 2 plus another half of a root 2 is a whole root 2, and then minus 1. You could leave your answer like this, or you could distribute and have 2 root 2 minus 2 as your answer. Okay. But on an exam, show me this intermediate step. If you jump straight from like here right to here, I don't really know how you got there. Okay, so please show me more work than you would in a regular semester, just so that you're covering your own bases and that I can clearly see how you get from one place to another. Okay. So let me go ahead and zoom back out. So this 2 root 2 minus 2 represents the area between y equals sine x and y equals cosine x from 0 to pi over 2. All right. Are there any questions on example 3?
When you took that integral, why is it minus negative cosine x?
Because the integral of sine x is negative cosine x.
Oh, okay, right. Okay.
Yeah. All right. Any other questions on example 3? All right. Well, if there are no other questions, then I'm going to have us go on a break. So it is 10:43 right now. Diana, if you want to pause the video and maybe we can all reconvene at 10:50. I don't think we'll have time to do. Okay. So let's take a look at example 6. So example 6 says, find the area of the region between the curves y equals 20 minus x, y equals square root of x, and y equals 1. And so we're going to start here with a diagram like we've been doing. And so I'm going to have my x-axis, and I'm going to have my y-axis. Okay. Now I've got 3 different functions this time, which is different, but let's take it piece by piece and see how we can handle this. So let's start with the orange one. Y equals 20 minus x. What shape is this function? And what are some important points or characteristics of this graph that we know?
Starts at 20 and goes down by 1.
It's up at, and it goes down by 1, exactly. So this would be a linear function. And so we could maybe draw this function like this. Okay. And we could label some of those points. So this one would be 0, 20. And this point would actually be 20, 0. okay? Because if I'm going down 1 over 1, down 1 over 1, I'm going to get to the x-axis at 20. All right. Now let's take a look at this green curve. Y equals the square root of x. All right, that is an important shape to know as well. So the square root of x starts at the origin and looks something like this. Okay. And now we've got one additional curve to take a look at, which is y equals 1. And y equals 1, we saw earlier, is going to be a horizontal line at y equals 1. And so that's going to be something kind of like this. Okay. Now, if I were to kind of shade in the region I'm trying to find the area of, it would be like this area right here. Okay, so that's what we want to practice visualizing, is that that's the area that we're trying to find. But I'm going to erase my shading so that I can think more specifically. Am I going to use vertical rectangles or am I going to use horizontal rectangles? Okay. So let's try the vertical ones first, because I see a 20 minus x, I see a square root of x, everything is in terms of x, so let me try the vertical one. So that first blue rectangle, what's the top curve?
Square root x.
It is the green one, yes, and the bottom curve is?
1.
1, okay. Does this second blue rectangle have the same top and bottom curve as the first one we looked at?
Yes.
Yes, okay. What about this one? Same top and bottom curve as the first two, yes or no?
Kind of.
Kind of, okay. What about this one? Same top and bottom curve as the other ones?
Nope.
No, okay. So that's really important to see, all right? Let me just draw those one more time. So this one has a top curve that's green and a bottom one that's purple. This one has a top curve that's green and a bottom one that's purple. This one, I think you're right to say, well, it's right at the intersection, so it could be orange or green on top. I'm not really sure, but the bottom is definitely purple. And then this last one, though, is definitely not like the others because the top curve is orange, not green. So what that means is that one of our options is to split our integral. So option 1 would be to have the integral from a to b of the green curve minus the purple curve dx. And then to that, you're going to add the integral from b to c of the orange curve minus the purple curve. And a would be right here. B would be right here where the orange and the green meet. And C would be right here. Okay, so one option is to do two different integrals. If we wanted to, okay, we could totally do this. And let's see what that looks like. So how do I find out the value for A? Like algebraically, how do I find the value of A?
set the green equation and the purple equations together?
Perfect. So to find a, we're going to say square root of x equals 1. And I square both sides, and I know that my a value is 1. So in my equation, I could say the integral from 1 to another number I have to find of that. Now, how do I find b?
Set B and C equal.
Yeah, we're going to set the orange curve and the green curve equal to each other. So we'll get 20 minus x equals the square root of x. Now, if I want to find that out, I would have to square both sides. So that would mean I'd have to FOIL this side. So 20 minus x squared equals x. And then after I FOIL, I'm going to move everything to one side, set it to equal to 0, and factor. So that would give me 400 minus 40x plus x squared equals x, or x squared minus 41x plus 400 equals 0. So from here, we would have to factor and see what we get in terms of things being equal to each other, okay? Now, if you wanted to factor, you would have to find numbers that multiply to make 400, but also add or subtract to make 41, all right? So what are some numbers that multiply to make 400, but could add or subtract to make 41?
$25 and 16.
25 and 16. All right, so x minus 25, x minus 16 equals 0. So I could say they cross at 16 and 25. Now, when I look back at the diagram, which one of these answers makes sense for that value? 16 or 25?
16.
16, right? Because it has to be less than 20, so it's going to be 16, not 25. So that means I can b value 16 and put that in there. Now that was a lot of work to find b, but it helped me with the second integral because I already know the bottom bound of the second integral. And to find c, I'm going to take the orange one and the purple one and set them equal to each other. Or I could say to find c, I'm going to set 20 minus x equal to 1. And that one is pretty straightforward. I think we'll get x equals 19. Okay. So I get to 19. All right. So now that we have those, before we take our integral, I'm going to suggest that we change this to x to the 1/2 minus 1 dx from 1 to 16. And the reason why I'm doing that is so that I can find my power rule. I know what my power is, okay? So we're going to go ahead and take this antiderivative for the first one. That'll give me 2/3 x to the 3/2 minus x. And I'm going to plug in 16 and I'm going to plug in 1 plus 19x minus 1/2 x squared. And I'm going to plug in 19 and 16. And so this is going to give me 2/3 times the square root of x cubed minus 1, plug in 16, plug in 1, plus 19x minus 1/2 x squared, and I'm going to plug in 19 and 16. All right. 2/3 of the square root of 16 cubed minus 1 minus 2/3 the square root of 1 cubed minus 1 plus 19 squared minus 1/2 times 19 squared minus 19 times 16 minus 1/2 times 16 squared. Okay. So 16 times 16 times 16 is the same as 16 cubed. Minus, this is going to be 2/3 plus 1 plus 19 squared minus half of 19 squared is going to be half of 19 squared. Minus 19 times 16 is going to give us 304 plus half of 16 squared is going to give us plus 128. And this will give me 2/3 times 4 times 4 times 4. This minus 1 and that plus 1 go away, so minus 2/3 plus 19 squared is 361 over 2, and then negative 304 plus 128 is going to be negative 176. And that's going to give us 4 times 4 times 4 is 64, times 2 is 128 over 3 minus 2/3 plus 361 over 2 minus 176, which is 126 over 3 plus 361 over 2 minus 171 over 6, or no, over 1, sorry, thinking ahead. But I do think a good common denominator here is over 6. So let's see, 126 times 2 is going to give me 252 over 6 plus 361 times 3 is going to give me 1083 over 6 minus 176 times 6 is 1056 over 6. So 252 plus 1083 minus 1056 is going to give me 279 over 6. Right? So one way of doing this problem is splitting it into two different integrals. But what that means is that we're doing two different things where we have to plug in numbers. And in this case, the numbers that we plugged in were kind of big. Like 19 wasn't a nice number necessarily. 16 wasn't necessarily a nice number. We had 3 different fractions at the end that we had to combine into one. Okay. So who likes this way? Anybody overwhelmed by this way? I am a little bit. I don't love this method. So let's do this. We're gonna take a look at our picture, and we're gonna take a look at a different way of framing the same picture, okay? So well, let's put that down here. So if I were to redraw my diagram from earlier, okay, I have my linear function. I have my square root function. And I have my linear function, the straight line that goes right horizontal. And we've already found some of these intersections. So for example, I know that this has a y value of 1, okay? And what I'd like to do is, instead of drawing vertical rectangles, I'd like to draw horizontal rectangles and see what happens. So because I know I want to see if curves have the same right or left function, let's draw a rectangle. So like this blue rectangle has a right curve, that is the orange one, and a left curve of the green one. This blue rectangle has the same right curve and the same left curve as the other one I drew. And so does this third rectangle. So because these are all have the same right curve and left curve, this actually is a great candidate for trying that with respect to x. Okay. So a few things that we need to do here. If we want to use this formula, we need C and D, which are y values. I also need my equations to be with y's. So I don't want my equations to have x's in them, but I want them to be a function of y. My C value is where I start counting the area along the y-axis. So that value is 1. Where I stop counting is here, because that's going to be where the very last blue rectangle is. Now I need to find out what this y value is, but that will be my D. Okay, whatever y value is, that's going to be my D. And instead of sort of stacking my rectangles along the x-axis, I'm going to be stacking my rectangles up the y-axis. Now the right curve here is the orange one. And the left curve here is the green one. But the way I put them in to the function or to the equation, that's not correct. Because I have a y value here, I have dy, and then I have x's in here. And so that means that my equation doesn't match. So I have to make it match. but I want to keep all the y values and I want to keep the dy. So what I have to do is change the orange one into a function of y, and I have to change the green one into a function of y. So let's take a look at the orange one first. The orange one is y equals 20 minus x. How do I isolate the x in this orange equation?
You just subtract the 20 and then you multiply by the negative to isolate x.
Yeah, so you'd end up with x equals 20 minus y. Okay? This 20 minus y, that is the same function, but in terms of y. And this is what you want to use inside where it says right function. Let's take the green function and let's do the same thing. I want you to isolate x. When you isolate x, what does that give you on the other side?
Y squared.
Y squared, okay? So y squared is what you want to put in instead of square root of x. And so when we do that, we will get our integral of 20 minus y, that's the right curve with respect to y, minus y squared, then that's the equation with respect to y. And that means that it matches the dy on the end. Now I know we found one bound earlier. We found this one to be 1, okay? And what I need to do is I need to find the top bound now. And to do that, I'm going to set my orange curve equal to the green curve, okay? But I'm going to use these two that I starred right here. So I'm going to say 20 minus y equals y squared. Now this is a quadratic, so I'm going to set everything equal to 0 and then factor. And so that will give me y squared plus y minus 20 equals 0, or y plus 5 times y minus 4 equals 0. Now I think we would agree these numbers are way nicer than when we had to factor the x squared minus 41x plus 400, the smaller numbers, right? These are so much smaller and much easier to sort of do quickly. This tells us that y can equal -5 or y can equal 4. So which one of those numbers is most reasonable to say d is equal to?
Four.
4. Yeah, because that number is clearly bigger than 0. So we're going to pick 4 as our d value. Okay. Now let's take this. Let's get rid of the parentheses. So the integral from 1 to 4 of 20 minus y squared dy. And let's find our antiderivative. So integral of 20 is 20y. Integral of y is 1/2 y squared. Integral of y squared is 1/3 y cubed. And I'm going to plug in 4 and I'm going to plug in 1. So this is going to give me 20 times 4 minus 1/2 times 4 squared minus 1/3 times 4 cubed minus 20 times 1 minus 1/2 times 1 squared minus 1/3 times 1 cubed. Okay, now very early on in that first example, I said I like to sort of group them by similar terms. And I'm going to do the same thing here, okay? What I mean by that is 20 times 4 is going to be a whole number, and so is 20 times 1. So I'm going to sort of collect those together. And this is going to be a fraction over 2, but so is this one. So I'm going to group those together. And then this is going to be some fraction over 3, and so is this one. So I'm going to group those together. So let me expand it first, and then I'm going to group by the colors. So I've got 80, because 20 times 4 is 80, minus 16 over 2, minus 64 over 3, and then minus 20, plus 1/2, and then plus 1/3. And again, these two I'm going to combine first. And then this, and this, and then this, and this. So 60 minus 15/2 minus 63/3. 60 minus 15/2 minus, this doesn't always happen, but 63 is divisible by 3, so that's going to be 21. So that'll give me 39 minus 15 over 2. And then I can say that this is going to be, let's see, 39 is going to be 78 minus 15 over 2, and that's going to give me 63 over 2. All right. So I'm sure that from the perspective of someone who is seeing this potentially for the first time, that both methods seem really, really long and really, really hard. Okay, that's totally fair. And let's kind of scroll back to our first option and relook at that. When I look back at the first option, I wouldn't choose to do it this way because right off the bat, I knew that I had to do 2 different integrals. And so immediately after I had drawn like my blue rectangles, the moment that I noticed I needed a second integral, I would have been like, I'm not doing that. And then I would have tried the second method right away without going through all of that work. That's the kind of decision making that I want us to sort of feel comfortable with. Like if you draw one picture and you're like, I don't want to do that method, then can you draw a different picture that supports your reasoning about why you're changing strategies? Okay. Now, I think that this second method for some folks is intimidating because for once in our lives, we're working with Y's and not with X's, and it's just not something that we're very used to. So we sort of write it off and we're like, well, I don't know, I'm just not going to do this method. But I would really encourage you to practice looking at which one is which and making sure you work through a few examples with the dy. And the reason is when we get to our next unit, 6.2 and 6.3, so our next two sections, we're going to be doing a lot of choosing which way we want to do things. And so if you only know one way and that's your only option, it really makes it hard to solve a variety of problems. Okay, so take the opportunity this week to master both dy and dx, and I think you'll find that very, very helpful when we go into next week where we're using this, but we're using it with an additional layer. That being said, are there any questions about example 6?
If you were to do it, since both ways are finding like the same area, should the area be the same?
Yeah, I believe they reduced to the same number. No? It is possible I made a sign mistake somewhere. Yeah, I'll go back and take a look at that. Are there other questions about number 7 or number 6 rather? Okay. So let's take a look at example number 8. Okay. So example number 8 is a good chance for us to practice that decision making. Okay. So example 8 says find the area of the region bounded by the curves x equals -9 plus y squared and x equals 7y minus y squared. So without even drawing any pictures, what are folks' instincts right now? Should we try the vertical rectangles or the horizontal rectangles?
Horizontal.
Horizontal. And why are you saying that? I would agree.
Sorry. Because there's y's in the equations.
Yeah. So we look at these equations, and as uncomfortable and unfamiliar as equations that are in terms of y are for us, sometimes they're giving us the equations in a specific way to say, hey, do the right curve minus the left curve, because that's what that's what's going to be easier for you. Okay. So let's take a look at what this looks like. If you have access to Desmos, let's go ahead and graph these. So the nice thing about Desmos is you can just type in the equation. So you don't have to solve for y first. You can literally type in x equals -9 plus y squared, and Desmos will give you a picture of that. The other way you can look at this is you can say, I know this is a sideways parabola because of the y squared, and I'm going to move the parabola 9 units to the left because left is sort of our negative when we go right and left, whereas like down is our negative when we go up and down. So when I put this into Desmos, or when I sketch a diagram of this, I'm going to see that I'm going to have a parabola facing this way. And I'm going to go ahead and label this point as not -9, 0 right now, because I just never really know when I'm going to need specific points. So like the more I label now, the less I have to label later. Okay. Now, if we use that same sort of reasoning, what shape is this second function, the green function?
Left facing parabola.
Mm-hmm. And check this out. We're going to even use a strategy we used earlier, which is factor. This means that this parabola, it does face left, but it's going to cross at y equals 0 and y equals 7. So that's going to look something kind of like that. And I think looking at the picture, most of us would be like, yeah, this is like a sideways looking picture, which makes sense because those horizontal rectangles, they have the right curve is green and the left curve is orange. This one has a right curve of green and a left curve of orange. Right curve of green, left curve of orange, and even this tiny one down here has a right curve of green and a left curve of orange. And that's great because as long as we can see the same curve on the left and the right the whole way, we only need one integral. So let's go ahead and write out our integral formula. So from C to D of the right curve minus the left curve dy. And I can even fill in my right and left curve right now. I know that I'm going to have 7y minus y squared as my right curve, and negative 9 plus y squared as my left curve dy. Now I just have to figure out my bounds. Now C and D are going to be y values. And again, I know that because I have a dy, I have a in terms of y, I have in terms of y. So this point is going to be my C value. Whatever that y value is my C value. And this point, whatever the y value is, that's going to be my D value. Now, I think like some of the other ones we've seen, these bounds are not necessarily obvious. So we're going to use our strategy of set the green curve equal to the orange curve so that we can algebraically find out where their intersection is. So to find C and D, we're going to set negative 9 plus y squared equal to 7y minus y squared. And I see some things to the second power, so I'm going to go ahead and move everything to one side, set it equal to 0. So I've got 2y squared minus 7y minus 9 equals 0. And I'm going to factor. So 2y and y are the only way I can make 2y squared. And now I have to think about numbers that multiply to make 18, but add to make 7. And I think I can say that it is 9 and 1. And it's going to be negative 9 and a positive 2 to get me that minus 7y in there. That means that one of my intersections is going to be at 9/2. And the other intersection is going to be at negative 1. This is your C value. This is your D value. So negative 1 to 9/2. All right. I'm going to give you folks a moment to practice simplifying this integral, finding your antiderivatives, and starting to plug in your bounds, okay? And in a couple minutes, I'll start to put up my work as well. So go ahead and start simplifying this, distribute what you need to distribute, make sure you take your antiderivatives. Is this what folks are getting? I think this is not correct. All right, let's start with this top part here. When you took away the parentheses and you combine your like terms, do we all agree with this step here?
Yes.
Yes,
Yeah.
okay. When we take our antiderivative or our integral, do we agree with this step?
Yes.
Should it be 7/2y squared?
Yes, indeed. Yeah, that squared has to be there, right? When we're taking that antiderivative, we want to make sure that we increase the power by 1 if it's a power rule situation, right? So unfortunately for me, my mistake was very early on. But one of the nice things about kind of writing out each step is it's a little bit easier for me to kind of go back in and find out what numbers to change and which ones I can keep by themselves. So for example, I know that this second 9/2 needs to be squared, okay? And that this -1 here also needs to be squared. So let's see what that changes on the next line for me. That's gonna change this fraction. So what is that fraction going to be? 7 times 9 times 9 is gonna give me 567 on the top, and 2 times 2 times 2 will give me 8 on the bottom. Now, when I changed everything to a common denominator of 24, that's going to change this one as well. So to change that to a denominator of 24, I'm going to multiply top and bottom by 3. And that should give me 1701. Okay, what does that change about the second term? Well, this is going to be positive, but when I distribute that negative, that means this is going to be negative. And that means that in the next line, when I change that to a fraction over 24, I have to subtract that fraction. Okay. So let's redo. I'm going to add my fractions again. 972 plus 1701 minus 1458 plus 216 minus 84 minus 16. And that's going to give me 1331 over 24. And that, I believe, should be the correct answer. Okay. So, what's up? All right. Anybody have any questions on this one? All right. So here's what we are going to do in our last few minutes here. All right, so I'm going to recopy question number 7 down here because I had crossed it out earlier. But it is a find the area, like the other question, enclosed by these two functions, y equals x minus 1 and y squared equals 2x plus 6. All right, so if you are still on this Zoom call, I'm going to ask you at the end of this to take a picture of your question number 7, all right? And you're going to send that to me. There's no official link on Canvas, so you're just going to email this to me, all right? You're going to email this to me right after we sign off the call. Whoa. Okay. So if you want to start on a new paper, that's totally fine. However you want to do it is fine. But let's go ahead and set this up. So I'll give you a few moments to kind of sketch a graph for this, all right? Think about what the graph is. Let's check that over together. And then we'll talk some strategy, like do we think this is a dx or a dy situation? And what is our reasoning for that? All right, someone tell me about the shape and some important features about this orange curve here.
It's a line.
Positive slope or negative slope?
Positive.
Positive slope and y-intercept?
-1.
-1, beautiful. All right, so we've got something kind of like this, okay? All right, this one, someone else who has an idea on important features of this green curve?
Right facing parabola.
Sure is a right-facing parabola. And this one is actually shifted 3 units to the left, okay? So we end up with like this kind of situation. All right. So what are our thoughts? Do we think this is a case of vertical rectangles or horizontal rectangles?
Go either way, right?
All right, let's see. So if I start with the vertical ones, top curve is orange, bottom one is green. Nope, other way around. Top one is green, bottom one is orange. All right, another rectangle, top one is green, bottom one is orange. Top one is green, bottom one is orange. Top curve is green, what's the bottom curve?
I take that answer back.
Yeah. Right? So when you're drawing these, make sure you test a variety of places in the diagram, right? If you only draw the ones on the right-hand side, I'd be like, yeah, we could do just two top minus bottom. But the tricky part is sort of the end of the parabola, because those last two green ones, or last two blue rectangles I have, are a situation where it's one curve minus itself, okay? And so for that reason, we're gonna undo this, and we're gonna say, let's try a horizontal rectangle and see what that gives us. So right curve is orange, left curve is green. Right curve is orange, left curve is green. Right curve is orange, left curve is green. And let me try right up here. Also a small rectangle, but right curve is orange, left curve is green. Okay? So as soon as you find a convincing argument for that, then you can say, all right, I don't want to deal with more than one integral. And so for that reason, I'm going to choose with respect to y. Now, if we are trying to find the intersections here, all right, I think we have to do a little bit of work. So what I might do is actually take my orange curve, which is y equals x minus 1, and I'm going to isolate x. So I'm going to get it in terms of y, and so that'll give me a y plus 1. And this is what I can put in for the right curve. So for the right curve, I'm going to put in y plus 1. Now let's rewrite our left curve. So y squared equals 2x plus 6. If I want to isolate x, I could subtract the 6. So 2x equals y squared minus 6. And then I'm going to divide by 2. And so this is what I can put in for the left curve. Okay. Now, the nice thing about doing this first is now I can set my orange curve and my green curve equal to each other, because they're already both equal to x. So I can say that y plus 1 is going to equal 1/2 y squared minus 3. And so this is the setup we're going to use to help us find our c and our d. And so I'm going to go ahead and multiply everything by 2 so I can get rid of this fraction here, because I think factoring is hard enough, and when you layer in fractions, you're like, it makes it even harder. So that's going to give me 2y plus 2 equals y squared minus 6. I'm going to move everything to one side, set it equal to 0. Y squared minus 2y minus 8. Y minus 4, y plus 2. So that means that my two values where the curves intersect are at y equals 4 and y equals -2. When I go back up to my problem, I'm going to put the -2 at the bottom, because I start counting from the bottom and I go up. And then I know that my top bound is 4, because that's where the curves stop intersecting. All right. All right. So I'm going to have you go ahead and finish this problem. Okay. And you're welcome to sign off and finish it on your own and then email that to me, or you can stay on until noon and I'm happy to help clarify any questions that you might have, but you just didn't want to ask in front of the whole class. But I'm going to ask that you email this to me by 12:30. All right, so it's 11:52 right now. I'm going to ask that you email this to me by 12:30. Let me zoom back out a little bit so you can see the whole of the work that we've done so far.
Where did you get the 2 from, Professor? I'm confused on that part.
Which two?
So when you distributed that 2,
Oh, this one?
yes.
Yeah, I didn't want to factor with a 1/2 in front of my y squared.
Mm-hmm.
So I was like, let me just get rid of the fraction. So I just multiplied everything by 2.
Oh, okay.
All right, so if I had like 1/4, I could multiply everything by 4. Boom, fraction's gone.
Okay.